In order to make an approximation of the proportional distribution, we should remember that it is just another way of interpreting a binomial distribution. We will start with a binomial distribution where n equals 24 and p equals 0.5, making q equal to 0.5 also. Recall that q is the probability of failure and is equal to 1 minus p. This is the equation used to calculate the probability of each value of x, and results in this binomial distribution. The mean of any binomial distribution is n times p. For this binomial distribution, the mean equals 12. The standard deviation of any binomial distribution is the square root of n times p times q, and for this binomial distribution, the standard deviation equals 2.4495. For this example, we will determine the probability of x being greater than or equal to 12 and less than or equal to 16. This is the same as finding this area. Using this equation, we can calculate the probabilities of x equal 12, 13, 14, 15, and 16, the probability of x being greater than or equal to 12 and less than or equal to 16 is 0.5486. Under the equivalent normal distribution, the comparable area extends from 11.5 to 16.5. Using the correction factor discussed in the previous video, the comparable probability is x being greater than 11.5 and less than 16.5. Remember, in the binomial distribution, the x values of the horizontal axis represents the number of successes in n trials. In the proportional distribution, we are interested in the probability of the portion of successes out of n trials, so all of the x values are divided by n. The mean of a proportional distribution is the mean of the binomial distribution divided by n, which is n times p divided by n, which is p. For this proportional distribution, the mean is equal to 0.5. The standard deviation of the proportional distribution is the standard deviation of the binomial distribution divided by n, which is the square root of n times p times q divided by n, or the square root of p times q divided by n. For this proportional distribution, the standard deviation equals 0.1021. The lower limit of the binomial probability was 12. It is also divided by n, which is 24, making the lower limit of the proportional probability equal to 0.5. The 16 of the binomial probability's upper limit is divided by 24 for an upper limit for the proportional probability of 0.67. The probability remains the same. The correction factor for the proportional distribution is plus or minus 0.5 divided by n. With n equal to 24, the correction factor for this distribution is plus or minus 0.5 divided by 24, or plus or minus 0.0208. Subtracting this from 0.5, we get the lower limit for the normal distribution of 0.4792, and adding 0.0208 to 0.67, we get 0.6875 for the upper limit. These values correspond to the left and right sides of the shaded area on the graph. We can now use these values to determine the probability in the normal distribution, which should approximate the probability in the proportional distribution. We need now to calculate the z-scores for the limits of the normal distribution probability. Recall the equation for calculating the z-score. For z1 of our example, we'll take 0.6875, the upper limit of the probability, and subtract from it the mean of the proportional distribution, 0.5, dividing the result by the standard deviation of the proportional distribution, 0.1021, for a z-score of 1.84. For z2, we'll use the lower limit of 0.4792 and subtract from it the mean of the proportional distribution, 0.5, then divide the difference by the standard deviation of the proportional distribution, 0.1021, for a z-score of minus 0.2. We will use the positive z-score table to find the area to the left of 1.84. which is equal to 0.9671. We next move to the negative z-score table to find the area to the left of minus 0.20, which is 0.4207. The area to the left of z1 is 0.9671, which is also the area to the left of 0.6857 in the normal distribution. The area to the left of z2 is 0.4207 and is also equal to the area to the left of 0.4792 in the normal distribution. The difference of these two values is 0.5464 and is equal to the area between 0.4792 and 0.6875 under the normal distribution. It also equals the probability of x falling between 0.4792 and 0.6875. When we use a computer function to calculate this, we get a slightly different value due to the fact that the z-score table only allows values with 2 places to the left of the decimal. In either case, using the normal distribution to approximate the proportional distribution seems to work rather well, provided the underlying binomial distribution meets the criteria n times p is greater than 5 and n times q is greater than 5. As with the binomial distribution, the proportional distribution loses symmetry as p moves away from 0.5, resulting in a less reliable approximation.